Hello world, in today's episode we are going to talk about one important aspect of loss function which is called regularization, and we are going to be focusing more upon this. So note that this is the second part of loss function series, so make sure you have watched the first one before watching this. So first of all we are going to focus upon L1 regularization and then L2 regularization, which are one of the most important techniques used to prevent overfitting as well. Then the third one is elastic net, in which we make use of both these L1 and L2 regularizations. Then Maxpooling is commonly used in neural networks, and I've talked about a lot in my previous videos on CNN, so make sure you watch that. And I've made a separate video on dropout regularization, and I've gone into details of what really happens when you use dropout. So feel free to check that video out before watching this. And if you watch this, we are good to go. So let's say you are going to implement logistic regression and you have this function J which takes in the parameters W and B. So this W over here is a high dimensional vector and B is just one parameter, and your objective is to minimize this cost function. What are we going to do? So I've talked about adding regularization parameter to it, and that's what we do. So this W over here is a high dimensional vector and B is bias vector. So we add this parameter over here, lambda is called the regularization parameter, and we divide it by 2 because it performs well. It gives a better performance when it comes to applying gradient descent. And over here W is a high dimensional vector again, and what really happens is that your loss function, your model, may have access to polynomial functions, and adding this regression penalty makes your model to prefer lower degree polynomials, so that if you train your neural network for a while, what really happens is that your model comes up with more complex decision boundaries and it may perform poorly on a testing set which we haven't seen across. So adding this regression penalty over here forces your cost function to use lower degree polynomials. It's like you have to overcome me in order to use those higher degree polynomials. So it's like a restriction which we are putting. And so this value of W square, it's equal to Wj square summation j is equal to 1 to nx, which is also equal to W transpose W. And so let's talk about L2 regularization. So in L2 we penalize the Euclidean norm, and here is L1 regularization. So note that there is a difference between both these, and what L1 regularization does is that it increases sparsity in the matrix. So if you have a matrix, if you have a vector with different elements, what's it gonna do? It's gonna introduce more zeros to your matrix, so it's gonna concentrate majority of the value at one side of the matrix and it's gonna introduce zeros, so you're gonna end up with sparse matrix. On the other hand, what L2 regularization does is that it distributes the value in the whole vector equally. So anything that you do to your model that penalizes the complexity rather than trying to fit the training data. So it measures the complexity of your model. And this B over here, which we omit, the reason why we omit this is because this cost function is a very high degree polynomial, and this over here is also not it's also a high degree as compared to this B, and so it really doesn't matter if we are using it alongside in it. So if we have a vector like this over here x, and we have equal elements, and what L1 regularization does is that, as you have seen, it increases sparsity, so we are going to end up with 3 zeros over here and it's going to concentrate the value at one side. What L2 regularization does is that simultaneously distributes the value of the elements. So and if you apply it to neural network when you're either using NumPy or a deep learning framework, this is how you do it. So this NL, L is this number of hidden layers we introduced, and M over here is the number of training examples. So L2 regularization is also known as weight decay, because when you are using backpropagation, it's also called Fourier norm. So when you use backpropagation and when you're updating your weights using this learning rate, and when you compute gradients, and when you simplify it, so this WL over here will be simplified and it's gonna come out of the bracket. So you're gonna be end up with something like 1 minus alpha times one expression. So eventually what you are doing is you're decaying the weight after every iteration. So let's talk about one important aspect, softmax. So it's often used in multinomial logistic regression. So earlier when we were using SVM laws, we just computed the true label, and after we got to know which label, which that image belongs to which class, we were not worried about more upon that. But in this case, softmax, we actually output the whole probability distribution, and we'll actually care about the true labels and we interpret it further. So SVM or softmax regression generalizes logistic regression to C classes rather than just to classes. So it's often more commonly used in multi-class classification. So as let's take an example over here. Suppose you have 8 classes over here, right? And you want to check which you input an image to your model and you want an output, which class does it belong to. So this is an example of multi-class classification, and what we do is, after we make this whole neural network over here, C is the number of classes over here. So in this case we have 4, and each one over here, this layer, it's going to output a probability which indicates that this image belongs to this class over here. So we take out scores. In this case what we do is we take out scores, exponentiate them so that they become positive. So over here, let's take an example. Let's suppose this vector, this we are calling it ZL. So it's a 4 by 1 dimensional matrix because we have 4 classes over here, and let's say the value of this vector is 5, 2, minus 1 and 3. So what we do is we exponentiate them. So e raised to the power 5, e raised to the power 2, e raised to the power minus 1, and so on, so that all these values become positive, right? And then we take a sum of the weights and then we divide it. So what's happening here is we are going to be ending up with this probability distribution over here. So it's often used maximum likelihood to estimate, and we take out scores, exponentiate them so that they become positive. We normalize it by we are normalizing it by sum of exponents. So we end up our scores to softmax function, and when we end up with this probability distribution over here. So whichever is highest, it gives the answer which class is it highly likely belong to. So probability of true class is I and is also close to 1, and just it's mathematically proven that log function, this log loss, it's very easy to maximize it if you were to compare it with the loss function. And we put a minus sign over here because if we maximize the loss function, log loss, if we maximize it and then we put a minus sign it, because this loss function gives how bad our classifier is, it doesn't tell us how good it is. So when you put a minus sign over it, it just clearly indicates it's very easy, it becomes very easy for us to minimize it, and it's tell us how bad the classifier is and how is it functioning over anomalous log classes over here. Note that log is a monatomic function, and where it's very easy to maximize it, so we put a minus sign over it, so it becomes very easy for us to minimize it. And over here we have this weight vector over here, we exponentiate it, then we normalize it using the sum of the values or the exponents, and then we end up with probability distribution over here. So this is the formula which we use. I hope it makes this video makes you clear how you can what Softmax classifier does. And this is a comparison of SVM and cross entropy laws. So in SVM, what we were doing is, previously we were just computing the true label, we were outputting a probability, or right, so we were just using this max 0 comma some value function over here, and whichever value predominates, that's the answer. So we were earlier we were not giving much values to the scores. If the predicted label were true, then we didn't go much further. But in Softmax, we use this probability distribution over here. So it tries to push the probability of the true labels more and more. So this probability distribution is makes our work very easy when it comes to multi-class classification, and it's used across whole of deep learning in the output layer when it comes to classification. So I hope this section of videos makes it clear of what loss function is and what effect does regularization have on loss function, and what you can do to prevent this overfitting. And we have discussed Softmax regression classifier, what it really does. So let me know in the comment section below how did you like, and what did I miss something. And please hit the like button if you liked it, and please share the video across your friends who are learning deep learning or machine learning, or who are just starting out with this amazing branch of CS. Please subscribe to my channel. Thank you. Talk to you in the next one.